Hello students, myself Nimesh Prabhakar. Welcome to Process, Dynamic and Control lecture series. In my previous lecture, I discussed about the distillation column. That means control of distillation column. In that lecture, we discussed about the overhead composition control. Then after we discussed about the bottom composition control. And then after we discussed the both product composition control. Now, in this lecture, we will discuss about the internal reflux control. Then after we discuss about the lag in the liquid flow. So, in this lecture, we discuss mainly two topics. First one is the internal reflux control, and then after we discuss about the lag in the flow. Now we start with the internal reflux control. Cold reflux has the same effect as the cold feed. It generates a small additional quantity of reflux at the point when it is introduced. This additional reflux is important when the reflux ratio is high and product flow is small. Now we understand this sentence by help of this example. So we get better understanding. So now we understand. So here we consider a case where the vapor flow in the column is 550 mole per hour and the external reflux is kept at the 500 mole per hour. Now if the reflux is at boiling point, there is no extra condensation and the product flow is 50 mole per hour. That means what this sentence is saying, if the reflux at the boiling point, then there is no extra condensation is needed. Now we understand the changing. So if the reflux is subcooled at the 10 Fahrenheit, about an additional 20 mole per hour is condensed in the column. The flow of vapor to the condenser is reduced to 530 mole per hour due to the change in the temperature, and the product flow dropped to the 30 mole per hour. So the reduced product flow would affect the product quality and would eventually be corrected by the compensation controller. So here, by using this example, we can understand the importance of internal reflux control. So, but the meanwhile, some off specification product would have been produced. So here we require specific control for the internal reflux. So here we understand the method of controlling of the internal reflux. So now, see, this is the first one, method of controlling of the reflux. So here this is the diagram of this method. So here this FC is indicate the flow controller, TC indicate the temperature controller, and LC is indicate the level controller. See here we use the fan. So now we understand how it works. So control of reflux temperature was formally accomplished by the manipulating the fan pitch as shown in figure. So here we control the reflux by manipulating or by changing the pitch of the fan. So the temperature in the reflux accumulator cycle with the period of the about 40 minutes and amplitude of the 5 degree Fahrenheit. The system is not self-regulating. Since a decrease in the reflux temperature leads to decrease in a vapor flow and thus a further decrease in the reflux temperature. So this is the drawback of this particular method. So here the system is not self-regulating. Now in this particular case, control is made worse by the large holdup and incomplete mixing in the reflux drum. So measuring the temperature at condenser exit would have given better control. So now we discuss about another method of controlling the reflux. Here in this slide we see there is some disadvantage or there is some limitation of this method of controlling the reflux by manipulating the pitch of the fan. So now we discuss about another method. So see, this is the diagram of the second one method of controlling the internal reflux. So here in this system shown in figure, the measured degree of subcooling and external flow are used to calculate the internal reflux and keep it constant. Now we understand here by using this diagram. Here in the diagram we can see the measure of degree subcooling and the external flow are used to calculate the internal reflux and keep it constant. The internal reflux is a linear function of a degree of subcooling. So we can write the relation between the R internal, that means internal reflux, and external reflux as R internal is equals to R external into bracket 1 plus K into delta T. Thermocouples measure the difference between the top temperature and the reflux temperature, and the difference is converted to the pneumatic signal. The square root extractor give a pressure proportional to the internal reflux, which is used as the input to conventional controller. The reflux temperature is measured just before the reflux enters to the column to avoid a time delay in the control loop. So here in the diagram, that means in my previous slide I discussed about the diagram. So here the reflux temperature we measure just before the reflux enters to the column to avoid a time delay in the control loop. So here we avoid the delay that is produced due to the measuring process. The control adjusting the pitch of the fan was eliminated in the other installation, and satisfactory control of the product flow obtained in spite of a large change in the reflux temperature. Now we discuss about the type of legs in the distillation column. Now we complete the first phase of this chapter. That means in the first phase we discuss about the controlling system. That means we discuss about the bottom composition control, then after the product composition control, the pressure control and reflux control. Now we discuss about the leg. So which are the legs that produce in the distillation column that we discuss here. So first of all we discuss about the type of legs. The largest leg in the distillation column are the concentration leg, arise from the capacity in the liquid held on the plate. So first one and the largest leg is the concentration leg that arise from the capacity in the liquid held on the plate. Now the next one largest are the leg in the liquid flow rate resulting from the change in the holder with flow rate. So we can say the capacity of the plate for increase the holder. So this is the second one, leg. Now we discuss about the third one. The still smaller and the often negligible are the leg in the vapor flow rate, which arise because the vapor holder increase with the pressure and thus with the flow rate. So here we can neglect the effect of this leg because this is the smaller and we can negligible. This is the leg, name is known as the vapor flow rate leg. This arises because of the vapor holder increase with the pressure and thus with the flow rate. Now the fourth one type of leg is the concentration leg associated with the vapor holder can be neglected. So here this is the fourth type of the leg that occur in the distillation column. Now we discuss about the first one type of the leg, that means the leg in liquid flow rate. This is the important question as per the GTU point of view. So here we discuss about the leg in the liquid flow in the distillation column. So the hydraulic leg for the liquid flow can be treated as a liquid level problem, which is complicated somewhat by change in level across the plate. At the center of the plate, the equivalent depth of the clear liquid is usually less than at the either end and may even be less than the well height as the shown in figure. So here from this figure we can see at the center of the plate the equivalent depth of the clear liquid is usually less than the either end and may even be less than the well height as shown as in this figure. So the height above the exit well edge and the average depth HT must increase with flow rate. If the effect of vapor flow changes is neglected, the material balance equation is right as A dHT by dt is equals to delta L in minus dL out upon dHT into HT. So this is the material balance equation for the leg in the liquid flow. So this equation we can write as the A dHT by dL out into dHT by dt plus HT is equals to dHT upon dL out into delta L in. So the time constant is the area times the rate of the change of average depth with the liquid rate or just the rate of change of holdup with the flow rate. So we can write time constant as TL is equals to A dHT by dL out. So we can write or equivalent to time constant as dH upon dL. So here this TL is indicate the hydraulic leg for the plate 1 and the H is indicate the holding of liquid per plate and this L is indicate the liquid rate. Now to get some typical value of TL, publish holdup data for the bubble cap plate operating with air and water are plotted in the figure. So here by using this graph, so we get some typical value of TL. published in the hold-up data for the bubble plate operating with the air and water. So the clear liquid height is obtained from the static pressure at the center of the plate and is slightly less than the average depth HT, but the difference is assumed to be small. The time constant does not depend on the width of the flow path. So the 1 feet width section of the tray is used for basis. For the tray width liquid part 5 feet long, the time constant is calculated as Tn is equals to 5 into 0.05 into 7.48 upon 12. So we get the value of time constant for the liquid part for the 5 feet is equal to 0.156 minute, and for the tray of the 10 feet long, the time constant would be twice as greater, or we can say the value is the 0.31. So for the column 1 feet in diameter, the time constant would be only a few seconds unless the length of wear was much smaller than the width of the constant area. Time constant is roughly proportional to the column size D because the liquid rate varies with the D square. So here we discuss about the lag in the liquid flow. So in this lecture, first we discuss about the internal reflux control. Then after we discuss about the lag in the liquid flow. So in this lecture, we discuss about these two topics. Thank you.